also the cylinder head when the piston reaches at the top dead center. Okay, so as far as the IP is concerned, the indicated power, the power input to air is, this is the equation, n over n minus 1 m dot r t2 over minus t1, where n is the polytropic index. Okay, and n could be in between, or n is in between the 1 and also the k value or the gamma value, where gamma is the specific ratio Cp or Cv. And to get the T, we use the T2, we use the relationship between T and P. So this is the equation that we have, right? And then after that, we have looked in terms of the what we call as the mechanical efficiency, right? So we have two types of efficiency which is involved. It depend on what type of device or prime mover running the compressor. So the first efficiency that we have is the mechanical efficiency, and the second efficiency we look in terms of the efficiency of the motor or the electric motor or the engine we use. So therefore, in this case, the power input to the system or the power input to the air is equivalent to IP divided by the mechanical efficiency and multiplied by the efficiency of the motor itself, right? And then after that, we look at the what being called is the minimum, right? The critical minimum input of power into the air, whereby we know that the ideal case is where n is equal to 1, where when we have n equal to 1, then we have t equal to constant. So we are living with a power which is stated as the P iso or P isothermal. So this is equal to PV ln P2 over P1, which is equal to the P, the M, R, T ln P2 over P1. So this is power, therefore this is m dot, this is equal to dot. So when we look at the P iso, then we have another parameter which is called as the iso or the efficiency for P iso, or we call as the efficiency for isothermal, which is equal to P iso divided by the IP, to look how far between the minimum and the ideal case of compression we got with the T constant against the IP. So this is what we have looked for, right? And one more thing that we have looked also in for case 2, whereby for the case 2, we have the VC is not equal to constant. Why do we need the VC? Because we want to have a mechanical comfort. That is for to allow the expansion of different material when heat is integrated or heat involved in the compression process. Another one is to look at the VC because we want to have a gap, okay, or space for the valve, right? So what happened? When we had this type of volumetric efficiency, the VC, the clearance volume, then what we have right here, previously we have the M of air intake to the system is as MA, right? Then when we have this type of, this is for the case of VC equal to 0, but when we have the VC is not equal to 0, then the air inlet to the compressor is MA minus MD. Okay, so it's less air input, less of air of mass input. So that is the drawback of having VC is not equal to 0. Okay, so as far as the IP is concerned, the IP is still the same formula. The IP is equal to n over n minus 1 m dot r t2 minus t1, but in this case the m dot is equal to m a minus m d. Okay, m a minus m d. But for the VC equal to 0, your m is equal to m a. Right? You can refer to the PV. Right? Okay. Now I want to look at the diagram of the case for VC is not equal to 0. So this is our P diagram. This is our
Doktor, sorry mengganggu doktor.
ya.
Tapi suara doktor semakin lama semakin slow.
Ya ke?
Tak dengar mana. Tak jelas.
Let me try another earphone. Yeah. Let me get up. Can you hear me?
Yes, doctor.
Is it clear?
For me, yes.
Yeah, try again. Okay, guys, can you hear me?
Yes, doctor. Can doctor?
Yes.
Yeah, I cannot.
Yes,
I
Doctor.
have to- Okay, thank you very much. I will try to speak louder. Okay. All right. I don't think that I'm scolding you, tak ada, because of this. I don't know what happened to this audio system. Maybe I have to reboot my computer, then only it will be solved. But right now, I'm not going to reboot it. I'm going to continue with the lecture. Okay. Right. Boleh? Guys, please respond. Boleh?
Can
Dengar,
doctor. Can.
Boleh
Thank
doctor.
you very much. Okay, so this is our PV diagram. So this is the
Doctor, are you
cycle.
sharing your screen?
Sorry, again I forgot to share the screen. Okay, you see? Ada
Yeah.
Yes, I can.
Okay, thanks a lot. Ya, hidup ni kena ingatkan antara satu sama lain. Kadang-kadang saya ni terlupa lah. Dah tua. Okay, so this is A, this is B, the compression process, and then the B to C is the delivery process, and C to D is the expansion process due to the leftovers of air inside the clearance volume. Okay, so this is a VA, this is your VC, right? And then this is your P1, and this is your P2. Okay, this is what I'm talking about. The M dot A is equal to MA minus MD, this part, and that part. Okay, so in order to get what is the IP, which is the area of this shaded cycle, so the IP, the equation is still the same, n over n minus 1, m dot r T2 minus T1, whereby the T2 is still the same, which is T2 is equal to T1, P2 over P1, T1 multiplied by P2 over P1, power of n minus 1 over n, right? But in this case, the m dot A, the m dot right here is equal to m dot A minus m dot D. So this is the part whereby the induction of fresh charged air. So if you look in terms of per cycle, this is in terms of kilogram per second. But if you look in terms of m dot, for per cycle, this is equal to MA minus MD. Okay, and at this P1 condition, we can see that the P1 VA minus VD, this is equal to MRT1. This is state 1. This is what we can use at point A, whereby the P1 is equal to VA minus VD equal to MRT1. Right? So this is the first equation that we must know. And then after that, we look how do we relate the VA, the VC, the VD in terms of VS. Okay, so we want to put the VA or the VS in terms of VA minus VD and VC. Usually, the VC is given in terms of the percentage of VS. Let's say we take 5%, for example. So this is what we have. The VC is equal to 5% of VS. So this is equal to VS. Right? So if you want to find the VS, so we look at our PV diagram. Let's say we want to find VS. Okay, let's say we want to find VS. So in this case, we want to look for VS. Okay, bear in mind, we want to calculate what is VS. Okay, so if we look at the PV diagram, what is VS? The VS is the sweat volume. So our VS should be from this point up to this point. So this is the VS. Okay, that is our VS. And in this case, what is VS? VS is equal to VA minus VC. Okay, VA minus VC. That is our value of VS. which is equal to VA minus VC. That is equivalent to VS. Have another equation right here, which relates the VS, whereby the VS is equal to VA minus VC. As far as the value is concerned, we could have the VA minus VD at this point. Okay? So, if we have this VA minus VD in terms of a value, then we might have, or we might get the value of VS from this equation. So we need to put up back what is VA. So what is our VA? From this equation, we are having the VA is equal to the VS plus VC from this equation. Right? So in this case, we know that what is VS? VS is plus 0.05 VC, VS, and this is equal to 1.05 VS. So now we have put the VA in terms of VS. Now we have to change the VD. So to look at the VD, how we change VD in terms of VS, then we look the process from C to D. Whereby what we have right here, this is the P2, right, at point C, P2, BC, power of N, which is equal to the P1, BD, power of N. So if we look right here, the process from C to D, so this is C to D, whereby we have the polytropic expansion right here. This is a PVN is equal to constant, same thing for this A to B. The expansion and also the compression process is according to the polytropic. So what we have right here, the PC power of N equal to PD power of N. What is PC? PC is equal to P2. And what is PD? PD is equal to P1. So this is what we have. Okay? So this is what we have. So right now, we could write the VD. So the VD over VC power of N, which is equal to, right? So this is VD over VC equal to P2 over P1. Then we write VD as our title. So what is VD? The VD is equal to VC P2 over P1 1 over N. And again, we know that the VC is being put as the, in terms of VS, this is 0.05 P2 over P1 1 over N. Meaning that if we know what is the pressure ratio, we know the value of N, then we could have the VD in terms of VS. So now we have put the VD is a function of VS. So what actually we have for this value, then we got this VA minus VD in terms of function of VS. Okay? So right now, we need to know what is VA minus VD. So from here, from this equation, we could have our VA minus VD. So from that asterisk, what is VA minus VD? VA minus VD is equal to MRT1 divided by P1. Okay? If you have dot right here, please remember, in order to get the VS, we must change the volume per cycle. You cannot put in terms of per minute. because that won't give you the swept volume. So this is V dot, this is V dot, then to change, okay, to change the V dot, VA minus VD, what we do, the VA minus VD dot, we divide it by the N. So then we get here is in terms of meter cube per unit time. Let's say it's second. Right here, we get meter cube per unit or per cycle. This is what we want. Okay, this is what we want. Okay. So that is the case how to get the VA minus VD in terms of VS, in the function of VS, if we want to solve for VS. So right now, let us look back to our question that we looked before this. Last 2 days. This is the question. Okay, put it whiteboard. Okay, a single stage double acting compressor is required to deliver 14 meter cube of air per minute, measured at 1.013 bar and 15 degrees C. The delivery pressure is 7 bar and the speed is 300 rpm. This volume is 5% of the swept volume and the compression and re-expansion index is 1.3. Calculate the swept volume. The same thing, right? So remember, this value, okay, this value for double acting. So we might convert this per single act or for the one portion of the compressor. Okay, this is for the both side of the compressor because it's double acting. So in order to get the VS, we need to get, or we need to see only one side. Okay, only one side. Then we will get the VS. If you maintain this 14 meter cube value, then you will get 2 VS, both VS. But the question asks for only VS. So you need to make something here whereby you need to divide by 2. Okay? So if we put all the parameters given, the m dot is equal to, sorry, no. So the V dot right here is equal to 14 meter cube per minute. Then measured at the pressure of P1 is equal to 1.013 bar. And the T1 is given as 15 degrees C. Then we have right here the P2 is given as 7 bar. Then the speed N is equal to 300 RPM. Next one is given the VC in terms of VS, 0.05 VS. Okay, so we need to get our VS. The question asks for VS. What is our VS right here? Okay, so first thing we need to get what is VA minus VD. So VA minus VD, like I showed before this is dot equal to M dot RT1. Okay, so in this case, we know that what is the R value, what is the T1 value, then we need to define what is M1. How to get m dot. The m dot is based on what? We take at the point of 1. Okay? This is equal to PV over RT. So this is 1, 1, 1. This is dot. Okay? This is equal to, what is our P1? P1 is 1.101.3. I will put it in kPa because I'm going to use the R as 0.287 kilojoule. So meaning that the pressure I have to put in kilonewton or in kPa. Then multiply this by 14. But remember, we need to convert for one side. So this is 14 divided by 2. And then after that, you see that this is in minute. In minute, then we need to multiply again or to change from minute to second. This is for the conversion of the V dot. Okay, and then we put right here.
Sir, excuse me, sir.
Yeah.
Sir, we divide the 14 by 2 because of the double acting compressor, right, sir?
Yeah. We only
Okay.
need to see only one side.
Okay, sir.
The 14 is because you know that for a double acting compressor, the delivery is 2.
Yeah.
For one cycle, the delivery is 2 times. That's why we need to look only at one side. That's why we
Okay.
have to divide it 14 by 2.
Okay, sir.
Okay, and then the 60 is to change from minute to second.
Okay, sir. Thank you, sir.
Okay, 0.287 multiplied by your 15. 15 plus 273, how much is that? Anybody? 15 plus 273, how much is that?
288.
280.
288.
288.
288. Okay, 288. Okay, so be careful with the unit, right? So you get your m dot. In this case, you get your m dot in kilogram over second. So I need to show you all the unit that you need to put in to get m dot in terms of kilogram per second. So this is how you do, right? So once you have your m dot, what do you get? You get your VA minus VD, correct? So this is your VA minus VD, which is equal to the V dot A minus V dot D divided by N. Okay, so from here, you will get the VA minus VD, right? Once you solve your m dot, then you get VA minus VD dot. You get in terms of value. And this value you put in here, then you get your VA minus VD in terms of meter cube per cycle. Again, be careful with your unit. If you put right here, your m dot is in kilogram per second. Right here, you are going to get kilogram per second. Then you need to change your 300 divided by 60. Okay? So I think that is being shown. As far as I'm concerned right now, I want to show you the formula involved because all the figures is inside the text. So when you have your VA minus VD, then you need to put your VA. What is your VA? So VA is equal to your VS plus VC. This is equal to VS plus 0.05 VS. So we'll get right here your, as far as VA is concerned, you get your VA 1.05 VS. This will solve for this value, for that VA. Okay, then what you do, you put your VD in terms of VS. So again, what is your VD? Your VD, as what I have shown just now, is equal to VC P2 over P1 1 over N. Then you put in terms of 0.05 Vs. Okay. Your P2 is 7. Your P1 is 0.103. 1 over and the index of expansion and expansion and compression is 1.3 right here. Okay, 1.3. So you put here 1.3. Can someone calculate for me how much is that? In terms of Vs?
Is 0.2212.
Vs.
Yes.
How about others? Do you get the same figures?
Yes, sir.
Thank you very much. So now you have solved your VA and your VD. So what we have right here is VA minus VD, right? 0.05 Vs minus 0.2212 Vs. So you are getting one value in terms of Vs. And then what you do is equate this equation or this VA minus VD in terms of Vs into this value. Okay, this value. You equate that. Then once you equate, you solve for your Vs. Okay, from here, you know that your Vs is being solved. Okay, so that is what being shown right here. See? So this is your swept volume. Change it to VA equal to Vs plus Vc. So this is the clearance volume given. This is your clearance volume. See now, the VA minus VD is equal to 14 divided by that. This is your VA minus VD. So here you put in terms of VA minus VD, 14 divided by 300 divided by 2. Okay, now the 14 is maintained as in per meter cube. So you get your VA minus VD in terms of the per cycle. Okay, per cycle. Then again, this is your VD. We have done that. Then we get the VA minus VD 0.0233. Then you equate this in terms of your VA minus VD in terms of value. Then you get your swept volume. So this is your swept. Okay. Next one. The next question is to get what is your IP. Oh, sorry, the delivery temperature. So of course, the delivery temperature, we are going to use the formula of T, yeah? So T2 is equal to T1, T2 over P1 power 1 of, sorry, N minus 1 over N. So in this case, everything is given, then you get your T2. Next one is to get the IP, not mistaken. The indicated power. The power. So to get the IP is equal to N over N minus 1. Here you use M dot R T2 minus T1. I like to use this equation in terms of temperature. You can also put in terms of pressure over pressure, but be careful. Sometimes you mix up with the N value. This is also can be written as N over N minus 1 M dot R T1. This is P2 over P1 N minus 1 over N minus 1. You can use also this formula, no problem. But I like to use this formula. It's very, very neat because you have defined your T2. Right? And then again, you could be asked to get the P-ISO. Okay, the P-ISO. So you can get your P-ISO equal to m dot r t ln p2 over p1. So be careful, right? Right now, the m dot you are going to put the IP, the m dot you are going to put in terms of both m dot or single site. This IP. Guys, remember this one? We have divided by 2, right? So this m dot is the one side of m dot. Okay, only one side because we have divided by 2. But as far as the IP is concerned, here, if you use the same value, the m dot, then you need to multiply by 2. 2 m dot. Again, here also 2 m dot. Sorry. So please take note, because the m dot we have calculated before is for one side, but the IP is for both sides, for the compressor itself. Okay, for the compressor itself. Same goes for the PISO. The PISO also you have to multiply by 2 right here. And once we have determined the PISO, if this question asks for PISO, then what we do is to get, maybe most probably you'll be asked to get what is your isothermal efficiency, which is equal to the PISO divided by the IP. Okay, so this is the typical question. Okay, typical question for reciprocating a compressor. And if you do all the question asked and add up with the PISO, okay, and then maybe add up a bit on the mechanical efficiency, or maybe you add up a bit more in terms of the motor efficiency or the engine efficiency, then this type of question, the difficulties is treated as moderate. Okay, it's treated as moderate for exam question or for the test question. Bear in mind, take note, your test question, okay, the level is equally as exam question. Right? That is how you solve for the case 2, where the VC is not equal to 0. Very, very famous question to get the VS. And this thing what I have written right here is very, very routine. This is how you get your VS. Okay. Any question? Guys, any question? Okay.
No, sir.
Okay, thank you very much. No question right now. Going to the next part. This is just to explain that usually your petal valve or your valve is usually wobbling. Okay, is wobbling. So you won't get a very smooth type of delivery and intake. But in our case, the analysis is always assuming that the delivery process from B to C is at P constant, and for the induction process D to A is always at constant pressure. So a bit fluctuation because of the wobbling. Okay. Okay. Now we go for the volumetric efficiency. Why do we have volumetric efficiency? You know what is volumetric efficiency? The volumetric efficiency is the ratio between the actual air coming into the cylinder compared to Vs. Okay, compared to Vs. See, you still remember this is our Vs, right? Here is our Vs. The Vs should be from this point. Okay, the Vs should be from this point to this point. So this is our Vs. Okay. So is this actually the V going in? Is this actually the V going in? The actual volume that going into this cylinder is V M R T over P. It usually depend on the ambient condition. Okay, basically it's depend on the ambient condition. So your T and P is not the same as what we have at this part. Okay, at this part it's not the same, right? So usually the inducted air volume or mass going into the cylinder usually is reduced by this VC. Okay, by that VC. So the differentiate or the reduction on this value of V is being put in the volumetric efficiency. Right? So this is the official or the fundamental definition of volumetric efficiency. The mass of gas delivered divided by the mass of gas which will fill the swept volume at the free air condition or pressure and temperature. So the free air condition, meaning that what you have is the P and T of the ambient. Okay, P and T of the ambient. So this is the mass of air delivered, actually delivered, and divided by the mass if it will fill the swept volume. So in this case, for the mass of air delivered, so this is M, which is equal to P V over RT. It doesn't matter whether you are going to put M dot right here or there's no dot. If you put dot right here, then there is dot right here. Okay, so assuming that the P and T, this P and T is the ambient condition. Okay, and at ambient condition. Divided by M, one more M, this is equal to what? Assuming it's still the ambient condition, but it's being filled up at Vs, the whole Vs, divided by RT. Okay, so I'm using M dot, I'll be consistent, so this is also V dot. Okay, so let us differentiate between the M dot actual and the M dot fill the whole Vs. So I'm putting right here is S. Okay, skip S. And what we have right here, this is equal to M dot divided by M dot S. Okay, so if I put here M dot by M dot S, then I can also write the volumetric efficiency as this divided by this. Okay, this divided by this. You see here, this is P, this is R, this is T. The same P, the same R, and the same T. So D will be cancelled off. Okay, so this is P V dot over RT divided by P V dot S divided by RT. So what happened? Final equation will be V dot divided by Vs. Okay, so we could write the volumetric efficiency using two equations, either mass by mass or volume by volume. So this is the two equations that we can use. See right here? And for your information, I will really like to use this equation because it is written the definition is in terms of volume by volume. So it's related or tally with what is being called as the volumetric efficiency. It's not being called as the mass efficiency. It's called the volumetric efficiency. That's why I told you V over Vs. Okay. So for the case of Vc is equal to 0, we are always getting the volumetric efficiency as 1. Okay, for the first case. For the second case, the volumetric efficiency will be less than 1. Okay, this is what we have, right? This is what we have when our system having clearance volume. Okay, having clearance volume. You see, when there is no clearance volume, this is a clearance C. When there is no clearance volume, the volumetricity equals 1. You can try it. Okay, because the V is Vs. But when we have clearance volume, then our volume of mass of air inducted into the cylinder is going to be less. Okay, it's going to be less. So can have right here volume in use. Volume in use due to the clearance volume is VA minus VT. Okay, VA minus VT. So in other words, we also can write the volumetric efficiency is equal to VA minus VD divided by Vs. That is our value. Okay, guys? So remember what is our VA minus VD just now? What is our VA minus VD just now? Guys, remember? For that example just now.
MRT, sir.
Pardon? The value.
MRT.
The value. No, the value. VA minus VD.
0.82.
It's 0.82, right? It's equal to 0.82 Vs. So you divide by Vs, then times by 100, you are getting 82%. That is your volumetric efficiency. For the same example just now we have did, we get the VA minus VD is 0.82 S. Okay? So that is our volumetric efficiency. Okay? Guys, I think that is for today. So what I need to do right now is to get your link for your attendance. Chat. See your chat. Guys, your link for attendance I put in the chat. Okay, the chat box. Right? So that is your, please sign in, guys. Any question? So remember, now we have gone into 2 cases. After this, we are going to see the next case. Okay, the next case. So basically, what we have right here is the volumetric efficiency is because of the clearance volume. Okay, we have no clearance volume. If no clearance volume, the volumetric efficiency is 1. When we have the clearance volume, then the volumetric efficiency is less than 1. For other parameters, the P-ISO, the IP indicated power, okay, the formula is still the same. It's still the same. Any question, guys? Okay, I'm going
No, sir.
to give you, yeah. Okay.
No question, sir.
Sir, kalau yang graf yang tadi yang ada naik turun yang saya kata valve tu wobble, maksud dia ada gas yang leak ke sir?
Tak ada gas yang leak, cuma dia punya apa ni nak tunjukkan dia actual
Oh, okay.
actual condition, sebab kita anggap dia straight kan, sebab kita nak memudahkan analisis, so we assume SP constant lah. Actually this part is wobbling, the valve is wobbling. So but itu cuma nak terangkan keadaan sebenarnya bla bla. Dalam kes kita we assume as a constant pressure for ease of analysis. Okay,
Thank you, Doktor.
any other question?
Doktor,
Ya,
link attendance saya tak dapat.
dekat chat.
Tak ada saya tengok. Okay, ada.
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 Saya baru tahu tadi.
Sorry Doktor.
Tahu tanya kan. Any other question guys? Ada question? Yeah? Okay guys, kalau tak ada, let me bye-bye you all first. Before we dismiss. Okay guys, take care. See you next week on Monday, insyaAllah.
Thank you, Doktor.
Thank you, Doktor.
Thank you,
Thank you, Doktor.
Thank you, Doctor.
Thank you, Doktor.
Thank you.